Hey guys, very good evening everyone, and welcome to another session by 360DigiTMG. So we were in the process of learning about capital market analysis, and we have been discussing about various things pertaining to our data science, what we can implement in the capital market analysis. We discussed about CDA, data pre-processing. We discussed about applications of capital market analysis. We discussed about the k-means clustering, KNN. Today, we are going to discuss about the linear regression in your capital market analysis. So by the end of the session, we'll be taking up a National Stock Exchange data set pertaining to a company called as Infosys share market, and we'll be doing linear regression on that. Talking about your linear regression. Linear regression is one of the most easiest and most popular machine learning algorithms. It is a statistical method that is used for predictive analysis. Linear regression makes predictions for continuous or the real numeric variables such as your salaries or age or product prices, so on and so forth. So linear regression shows the linear relationship between a dependent variable and one or more independent variables. Hence, it is called as a linear regression. Since linear regression shows the linear relationship, which means it finds how the value of the dependent variable is changing according to the value of the independent variable. Suppose these are the data points. And this is the linear regression type. The linear regression model provides a sloped straight line representing the relationship between the variables. So these are nothing but your data points. And this is your line of regression. Say this is your dependent variables. And this is your independent variables. When we talk about the mathematical representation of linear regression, it could be given as y is equal to a0 plus a1 of x plus epsilon. Y is a dependent variable, that is a target variable. X is the independent variable, that is a predicted variable or predictor variable. A0 is the intercept of the line. A1 is talking about the linear regression coefficient, that is the scale factor to each of the inputs. And E is your random method. Sorry, the same thing is given over here. The linear regression model provides a slope a straight line representing the linear relationship between the values. If we see this image over here, mathematically we can represent, and all these values are given away. The values of x and y variables are training data sets for linear regression model representation. So, linear regression is a machine learning algorithm. Based on this supervised learning, it performs a regression task. Regression models a target prediction value based on the independent variables. And it is mostly used for finding out the relationship between the variables and the forecasting. Different regression model differs based on the kind of relationship between the dependent and independent variables they are considering and the number of independent variables that are getting used. When you talk about your regression line, see over here. Yeah, it is given. So when you are talking about your regression line, a linear line showing the relationship between the dependent and the independent variable is called as a regression line. A regression line can show two types of relationship. One is a positive linear relationship. Another one is a negative linear relationship. Up. So a linear line showing the relationship between the dependent variables that you see over here and independent variables is called a regression line. A regression line can show two types of relationship. One is a positive and one is a negative. So in positive, what happens is if the dependent variable, that is a y, increases on the y-axis and the independent variable on the x-axis is also increasing, then such relationship is termed as a positive linear relationship. But if you observe over here, as and when the values on the x-axis are getting increased, the value on the y-axis is getting decreased. That is called as a negative linear relationship. Our goal is to find the best fit line. That means the error between predicted values and actual values should be maximized. And the best fit line will have the least error. Different value for weights or the coefficient of lines, that is A0, A1, gives the different line of regression. So we need to calculate the best values for A0 and A1 to find the best fit line. And to calculate this, we use something called as a cost function. Even before we go there, when we talk about types of linear regression, we are having two types of linear regression. One is simple linear regression, one is multiple linear regression. If in a data set there is one dependent variable and one independent variable, then that is called as a simple linear regression. And when you are having one dependent variable and two or more independent variables, then that is called as a multiple linear regression. Okay. So we were talking about your cost function. Cost function, we know that for this A0 and A1, we need to calculate the cost function. The different values of weights or coefficients of the line gives the different line of regression. We understood that. And the cost function is used to estimate the values of the coefficient for the district line. The cost function, what it does is it optimizes, or you can say the cost function is used to estimate the values and it optimizes the regression coefficients, or it measures how a linear regression model is performing. And we can use the cost function to find the accuracy of the mapping function. Which maps the input variable to the output variable. This mapping function is also known as the hypothesis function. When you talk about linear regression, we use something called as mean squared error function. Mean squared error cost function, which is the average of squared error occurred between the predicted values and your actual value. And this is what is being talked about here. So, for linear regression, we use mean squared error cost function, which is the average of squared error occurred between the predicted values and actual values. And this can be written as MSE is equal to 1 of 1 by n sigma n of I. This is the form, where n is the total number of observations you are having, y of I is your actual value, and a1 of xi plus a0 is nothing but a predicted value. So this is your predicted value. Yi is your actual value, and n is the total number of observations. Then comes something called as your residual. A residual or if we say residuals, the distance between the actual value and predicted value is called as a residual. If we observe points are far from the regression line, then the residual will be high. And so the cost function will always be high. If the scatter points are close to the regression line, then the residual will be small and hence your cost. Another thing is your gradient descent. Gradient descent is used to minimize the mean squared error by calculating the gradient of your cost function. A regression model uses gradient descent to update the coefficients of the line by reducing the cost function. And it is done by, you can say, random selection of values of coefficient and then iteratively updating the values to reach the minimum cost function. When we talk about linear regression, linear regression has some assumptions associated with it. First, linear relationship between the features and the target. Linear regression assumes a linear relationship between the dependent and your independent variable. A small or no multicollinearity between the features. Another thing. So first is linear relation between features and target. Another thing is a small or no multicollinearity between features. Multicollinearity here means high correlation between the independent variables. Due to multicollinearity, it may be difficult to find the true relation between the predictors and the target variables. Or we can say it is difficult to determine which predictor variable is affecting the target variable and which is not. So the model assumes either little or no multicollinearity between the features and independent variables. Another thing is homoscedasticity. These are the various assumptions, guys, that I'm talking about, and homoscedasticity. And heteroscedasticity. When we talk about homoscedasticity is a situation when the error term is the same for all the values of the independent variables. So with homoscedasticity, there should be no clear pattern distribution of data in the scatter plot. Another thing is normal distribution of error terms. Linear regression assumes that the error term should follow the normal distribution pattern. If error terms are not normally distributed, then confidence intervals will become either too wide or too narrow, which may cause difficulties in finding the coefficients. It can be checked using your QQ plot. If the plot shows a straight line without any deviation, which means the error is normally distributed. Another thing is no autocorrelation. The linear regression model assumes no autocorrelation in error terms. If there will be any correlation in the error term, then it will be drastically reducing the accuracy of the model. So autocorrelation usually occurs if there is a dependency between residual values. Talking about the use of linear regression in the capital market, linear regression analyzes two separate variables in order to define a single relationship. We understood that. And investors and traders who use charts recognize the ups and downs of price printed horizontally from day to day, minute to minute, or week to week, depending on the evaluated time frame. The different market approaches are what makes linear regression analysis so attractive. So, if you talk about plotting the stock prices, if you are plotting the stock prices along a normal distribution bell curve, right? So it can allow traders to see when a stock is overbought or oversold. If you are using linear regression, if it is being used by a trader, you can say a trader can identify key price points like entry price, stop loss price, and exit price. A stock's price and time period determine the system parameters for linear regression, making the method universally applicable. So, technicians and your traders often work on one system for a particular security or stock and find the same parameters. Won't work on other securities or stocks. The beauty of the linear regression over here is that the securities price and the time period determine the system parameters. Using these tools and the rules defined with this article on various securities and time frames, you can observe that linear regression is again a very good thing to use for the capital market analysis. Okay. So to conclude, linear regression has been found useful in regression and prediction modeling due to fact that it can get accurate predictions and it can handle only continuous variables. The execution of the linear regression can't happen without correct dependent and independent variables. The thing that you should bear in your mind. So now let us quickly go to our Jupyter notebook, guys. And this is again the same data set that I've been using for the past couple of days. And this data set is from National Stock Exchange pertaining to Infosys stock market prediction. And let us see, we are trying to do the linear regression over here. So I'm importing the warnings over here. I'm importing the required libraries over here. So I'm importing pandas, numpy, seaborn, matplotlib, and so on and so forth. After importing all the libraries over here, I'm importing the data set also. So let me quickly show you the data set that I'm having. So this is the data set which I'm using. So it is having date as one column and opening as one column, high as one column, low as one column, close as one column, ADJ close, adjusted close as one column, and volume as one. So we are using this. And after loading the data, I'm storing it into a variable called as Infosys, and I'm saying Infosys.head. So this is going to give me my top 5 observations. Now, when you say Infosys.info, it is going to give you now all the information regarding the various columns that we will see. I'm checking for the null values over here. So I'm getting false, 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 so on and so forth. And I'm saying, give me the sum of your, missing values. So for the open, high, low, and close, I'm getting 1, 1 as well. Total 6, I'm getting the, missing values. I'm asking for the columns over here. So I got the column. I'm asking for the unique values in your date. So these are some unique values. And I'm asking for the unique values for open, high, low, so on and so forth. So I'm getting. I'm also taking the value counts over here for each and every column. So when we are using the value underscore count function returns object containing values of unique count of unique values. The resulting object will be in descending order so that the first element is the most frequently occurring element and it excludes your missing values by the default. So here I am trying to find the counts of your unique values. When we were using the unique function over here, if you observe, unique function I have used here to find the unique elements of an array, and it returns the sorted unique elements of your array. Right. So after using it, I'm getting the counts of these unique values. And then I'm saying Infosys.describe. So I'm getting the mean, standard deviation, 25th, 50th, and 76%, and so on. I'm dropping the missing value from the rows column. I'm saying access is equal to 0. When you say access is equal to 0, it will always refer to your rows. When you will say access is equal to 1, it will always refer to your columns by. So I'm dropping the missing value from rows, and then the values that I get, I'm storing it into a variable called as Infosys underscore. So when I say Infosys underscore, this is the data that I'm getting. Again, on this data set, I'm checking the cross-checking for the missing values. I'm asking for the sum, so I'm having 0 missing values. I tried to plot the heat map, but I guess there's something wrong with my Jupyter. It is not showing over here. Anyways, so what I identified was there is no missing values. Then again, I'm saying dot describe. I'm getting your count, standard deviation, and all these values. on this new data set, I'm getting your information over here. And now I'm changing the data type to date time. The data type that I'm having over here is an object date column, and I'm changing it to date time using your pointer, storing it into a same column date into your Infosys underscore new, and then I'm printing your data frame to stock markets between so on. So the analysis that I'm getting is that the data frame contains the stock prices between your, so many date time, and total days is your 1,825 days. Again, I'm taking the Infosys underscore new date dot minimum value, maximum value. I'm trying to use your data frame contains stock prices between so on. So I'm trying to print that. I'm also trying to print the total days. So again, here I'm getting this thing. And now using this information, which I had in my data set, opening column, high column, low close, adjusted close, I am plotting a box plot to identify the outlier. So this is the kind of box plot I'm getting. For each and every column, for open, for high, for low, for close, and for adjusted close. Now, I also try to figure a fair plot for all the columns. So when you talk about the pair plot that you see over here, pair plot is a pair-wise relationship in the data set. And the pair plot function creates a grid of axes such that each variable in the data will be shared in the x-axis across a single row and in the x-axis across a single column. And that creates plots as you are seeing over here. And it is a matrix of scatter plots that lets us understand the pairwise relationship between the different variables. So here we are having multiple variables, date, open, high. So we can, observe, this is a matrix, all these columns here, all these columns variables here. So I got your pair plot. Then I was checking for the collinearity. The reason why I was checking or even before discussing about that, when we are talking about the collinearity is a correlation between your predictors, variables, or independent variables such that they express a linear relationship in a regression model. When predictor variables in the same regression model are correlated, they cannot independently predict the value of the dependent variables. Right? So they are trying to express a linear relationship into your regression model. So I'm checking your collinearity over here. If we are having a collinearity problem, suppose we are having a multicollinearity. So whenever an independent variable is highly correlated with one or more other independent variables in a multiple regression equation, multicollinearity will become a problem because it undermines the statistical significance of your independent variable. So here I'm checking for your collinearity, and I'm using your heat map also over here. For that, I have simply taken the data set name and I'm saying CORR. So I'm also trying to plot it on the heat map over here. Now I'm trying to split the data. And for that, I'm importing your train test split from sklearn.model_selection. I'm importing your min max scalar. I'm importing your standard scalar. We already discussed about your mean squared error as MSE. I'm importing that. I'm also importing your R2. After that, I am splitting the data into X-train and X and Y testing and training data. And I'm taking the testing size as 30%, so the training size is of 70%. The random state I've taken as 101. And I'm saying a scalar I want to use as your standard scalar. And I am running this model on X_train. From the sklearn.linear, I'm importing linear regression. And I'm saying that whenever I say model, I want the linear regression to. I'm running your linear regression on training data. And when I get the accuracy score, I'm getting off 0.53, that is 53%. Now, accuracy with your linear regression, I was getting as 53%. So I'm printing the scores over here for the testing and for your model prediction on X train, Y train, so on and so forth. So these are the various scores I'm getting. For the training data, R2 score that I'm getting is 53%. For the training data and testing data, I'm getting as well 50%. And mean squared error, I'm getting as 5156. For training data and for testing data, I'm getting as 5062. When you're talking about your R2 score over here that you see that we calculated, R2 score is a coefficient of determining or coefficient of determination that you can see. And it is used to evaluate the performance of your linear regression model. It is the amount of variations in the output independent attribute which is predictable from the input independent variables you can say. All right. So when we calculated this, we are getting the accuracy score of Infosys stock market using linear regression, that is a 53% to DC. Okay. So what all things we understood till now? We understood about what is linear regression. Linear regression is nothing but a simple and powerful and mostly used algorithm in your data set. And it is used when we are talking about machine learning algorithm. So it is being used over there. And in the supervised learning, we have your classification and the regression problem. So for your regression problems, we are using your simple linear regression models. Linear regression models. And we discussed about best fit line. We discussed about cost function. We discussed about gradient descent for the linear regression as well. Right? And we did the hands-on for our this Infosys stock market that you are seeing over here. We discussed about the various assumptions that we had that we are having in our linear regression model. We discussed about types of linear regression, and there is one more thing that I would like to tell you people. There is a term called as overfitting. And multicollinearity we already discussed. So when we are talking about the assumptions that is made for your linear regression, it is still whatever assumptions that we are having for simple linear regression, the same assumptions can be made for your multiple linear regression as well. But when we talk about multiple linear regression, here we can use your overfitting, multicollinearity, and feature selection. These are few additional assumptions that can be added for our considerations of multiple linear regression. Overfitting, I wanted to discuss about. There is two things that you need to know, when you are working on the models. One is your overfitting and one is your underfitting. And even before that, bias and variance. Bias, assumptions made by the model to make a function easier to learn. It is actually the error rate of the training data. So when the error rate are high value, we call it as high bias. And when the error rate is low, then it is called as a low bias. Variance, on the other hand, is the difference between the error rate of the training data and testing data. That is why it is called as a variance. The difference is high, then it is called as a high variance. If difference is low, it is called as a low variance. Now, talking about underfitting. A machine learning algorithm is said to have an underfitting when it cannot capture the underlying trend of the data. That is, it only performs well on the training data, but performs poorly on the testing data. The underfitting destroys the accuracy of the machine learning model. Its occurrence simply means that our model or the algorithm does not fit the data well enough. And it usually happens when we have fewer data to build an accurate model. And also when we try to build a linear model with few non-linear data. In such cases, the rules of your machine learning model are too easy and flexible to be applied to such minimal data, and therefore the model will probably make a lot of wrong predictions. So underfitting can be avoided by using more data and also reducing the feature of your feature selection model. So the reason for your underfitting is high bias and low variance. Whereas when we talk about overfitting, overfitting is just the opposite of it. Means here we are having high variance and low bias. When you talk about underfitting, we can increase the model complexity to reduce your underfitting. And we can increase the number of features performing feature engineering. We can remove noise from the data and increase the number of epochs or increase the duration of training to get better results. Whereas when you talk about overfitting, here the ways that we can use to reduce our overfitting is that by increasing the training data, reducing the model complexity, and early stopping during the training phase. We can use rich regularization and lasso regularization as well. and use dropout for the neural networks to tackle your overfitting as well. So guys, this was all about our linear regression. Thank you guys so much for joining. I hope the session would be enlightening for you guys. Keep on practicing. Be safe. Tomorrow we'll be meeting again. Thank you so much, guys.